Okay, so we've covered proteins and enzymes. Now we're going to cover another important class of biomolecule, carbohydrates. This nice sugar molecule. I'm trying to cut down on sugar. That would be a good thing, right? We all should. I just look at how much sugar my kids eat, and that is just an amazing amount of sugar. It's crazy. Anyway, and they just want more. First, what we're going to do is look at the structures, then the chemistry, and then lastly, we're going to look at higher level structures. So again, let's just review. A carbohydrate is a compound of a ketone, right here, ketone, or an aldehyde with many hydroxyl groups. So that's where polyhydroxy. So polyhydroxyaldehyde, polyhydroxyketone, or a substance that gives these compounds when you break it down. It can be a simple monosaccharide that does not hydrolyze. What we mean by breakdown by water, right? That's right. Into smaller carbohydrates. Or it can be a polysaccharide. Okay? These are built on, we also call polysaccharides carbohydrates. These monosaccharides build our polysaccharides. They're polymers, right? Monosaccharides have the general formula where they have 2 times as many hydrogens as they do carbons, and the same number of oxygen as they do carbons. But the important thing is that we usually have from 3 to 8 carbons in our monosaccharide. Now, and they all either have an aldehyde or a ketone. So you have that carbonyl, that C double bond O, in all of our monosaccharides. So we have 2 types of naming systems. One is a general naming system, like a class of type of monosaccharides. And then we have like a common name for each monosaccharide. So we're going to classify them based on whether it's an aldehyde or a ketone. And then we're going to classify them on the number of carbons. And think of your shapes. Tri for 3. Tetros, I think of the video game Tetris. That had the boxes that would cause great anxiety in me.
Or would you click the box and then it would kill you?
No, the boxes would fall down from the sky and you'd have to fill it up. Getting as fast as you go. And yeah, no. Pentos, pentagon. Hexos, hexagon. So these are Greek prefixes for the numbers. So we name it as, if it has an aldehyde in it, that means the carbonyl is on the end. It's an aldose. If the carbonyl is the second one down, it's going to be a ketose. Do you think that the OSE stands for like a sugar? See that in all of us? All right. And then, so we put it together. So we begin with the prefix aldo or keto based on whether it has an aldehyde or a ketone. And then we end it with number of carbons. So an aldose with 3 carbons is called an aldotriose. A ketose with 3 carbons is called a ketotriose. So here, the aldose has the carbonyl on the end. The ketose has the carbonyl second one down. But what does every carbon have? An oxygen, right? Other than the carbonyl, remember carbonyl is this, C double bond O. Other than the carbonyl, every carbon has an oxygen, an OH. This N means that it repeats, or it can repeat. Now, let's take a look at this. What's special about carbon number 2 over here on the left? It's stereoisomer. How did you know that? It has 4 different groups. So we have the OH, the aldehyde, the CH2OH, and then the hydrogen. So that is a stereoisomer right there. So this molecule is called glyceraldehyde. That's what this monosaccharide's name is, the common name. But its classification is an aldo, because of the aldehyde, triose, or triose, whatever you want to say, because it's 3 carbons. This one, it's called dihydroxyacetone, but it is a keto, because it has a ketone group. The carbonyl is buried in the middle. And then it's a triose too because it has 3 carbons. Not too bad, right? So at this point, I would expect you to be able to classify not by the specific name, but by the classification name. So glyceraldehyde has 2 stereoisomer forms because this carbon number 2, is a stereocenter. 4 different groups attached. Now, we take the way we are writing them. Now remember, the way I'm writing these 2 is not accurate. What you can do in your notes and what might be helpful is to make the carbon here in the middle, make the ones that go right and left wedges, like the dark, so they're coming out at you. This, like, my body's the carbon, and my head is the top one, my legs are the bottom one, so it's like, it's really hard to do. So like the ones right and left are coming out, and my back and my legs are going back into the stomach. I don't know. Now you're going to remember that right now, right? Say, weird, Dr. Barron. It's in there. Sorry. All right. So that's how it really is. So you can put dashes up and down, dashes for up and down, and then the wedges, right and left. Now, with that in mind, with the wedges right and left coming out at you, actually, this is good too. Maybe this would have been more appropriate than my body, right? My hand is the carbon. My index finger is the aldehyde. And my elbows are the CH2OHs. So on the L isomer, the OH is my thumb. And then on the D isomer, the OH is on my thumb. Now try. Can we superimpose them to match up? Okay, that doesn't work, right? We can't superimpose them. So here you can see that non-superimposable mirror images are stereoisomers. We call this this carbon, sometimes people call it an asymmetric carbon. We call it the chiral carbon. All right. Now, how do you know which one is the D and which one is the L? If the OH is on the right-hand side with the carbonyl on the top. So what you have to do is put the carbonyl on the top, and if the OH is on the right, then it's the D. And if the OH is on the left, it's the L. That's convenient, isn't it? Having the most oxidized, yeah, L left. And doesn't the Spanish word for right start with a D? Yeah. I think it's the German, yeah. And the German word for right, I think, is also D. Olive is French, too, so it must be a Latin thing, right? Anybody take Latin? Aaron, you took Latin. Do you know what the Latin now? My daughter's doing an online Latin course. 6th grade.
Why?
No, because she's trying to like minimize the number of high school classes she has to take. Because she wants to play softball, so she wants to like be.
So my friend's daughter is taking Mandarin. She's 4.
She's 4. She's taking Mandarin. Wow.
Well, like that's her second language over Spanish and English.
That's awesome.
What's Mandarin?
Is it? Yeah.
That's awesome. Yeah. New world. All right. So the D, I like this. I think, oh, you can draw a D and pass through the OH. And then the L is on the left. All right. So this is easy for our 3 carbon one. So we're looking at the chiral carbon, and it's where the OH is. All right. So those are stereocenters, and that's what we're using to tell us whether we have the D or the L isomer. Again, here's a better look. I wish I remembered that I had this slide, because then I wouldn't have to do my gymnastics. And it really helps. So we say that the relationship that they have together are enantiomers. And again, the dashed go behind and the wedges come out front. Now, this is only for a triose, right? It makes it easy for a triose because there's only going to be 1 chiral carbon. But most of our monosaccharides that we're going to deal with have 5 or 6 carbons. So to say whether we have a D or an L, we put the, and we're going to go into this a lot, we're going to put the most oxidized carbon, the carbonyl, at the top or at the second one. So it's either going to be at the top or the second one. And then we're going to string it down. Again, the ones to the right and left are coming out at you. And the ones that are going up and down are going back. And so here we have D-glucose because we look at the what we call the penultimate carbon or the last chiral carbon and see where the OH is. So here is D. Now why am I only showing D? Why did I stop showing L's?
Biologically active.
Yeah, the D is biologically active. So most of the time when we draw monosaccharides, we're going to draw the Fischer projection because we are too lazy to draw out the wedges and the dots. Yes?
So you always look at the last carbon on the chain.
You know, look at the second to last because the last one is not going to be chiral.
Okay. So last chiral.
The last chiral carbon, yep. We're going to go over that quite a bit. So in our Fischer projection, we're going to put the most oxidized. What do I mean by most oxidized? The C double bond O. That's what I mean by most oxidized. Carbon as far up to the top as we can. So in an aldose, it's going to be the top one, and a ketose, it's going to be the second one. Now this numbering on this one, it's off. It should be carbon 1, 2, 3, 4, 5, 6. There's no carbon down here. I don't know why the numbering is just off. It doesn't match up. So we do number the carbons. All right. So here, the carbon that's dictating whether it's a D or L glucose or D or L sugar, I mean, is carbon number 5 because the last one is carbon number 6. We're going to talk about these numbers a lot. So get used to saying, oh, carbon number 1 is the oxidized carbon, is the carbonyl. So that's an aldose. Carbon number 2 is the oxidized carbon. So that's a ketose. Okay.
Carbon number 1, the most oxidized because it has the double bond.
Yes. Compared to the COH and a C double bond O, the C double bond O is more oxidized, has less hydrogens than the COH.
Does the naming vary dependent upon D or L?
No, but we're going to talk about what does L-glucose look like, right? So glucose, for right now, is going to be the only structure I'm going to ask you to memorize. And the way I look at it is you put the carbon, it's 6 carbon, so it's an aldohexose. You're going to put the aldo on the top, and you're going to do the 6 carbons down. And you're going to memorize right, left, right, right. Right, left, right, right. So an aldohexose, right, left, right, right. That's all you have to memorize when doing the structure for the Fischer projection for our glucose, our D-glucose. Yes? Jordan.
What's the configuration where you're like drawing it in a circle?
It's the Haworth projection, so we haven't gotten there yet.
Okay.
So we'll get there momentarily.
I could have swore I learned it as Fischer in Orgo. I don't know.
No, the open chain is, well, there is a Fischer projection, but we'll differentiate between those two, okay? Fischer projections are usually more,
The Newton's projection, the circle and like the line.
so most of the time we use Fischer projection for the open chain and the Haworth for the closed chain, but I can show you the Fischer projection for the closed chain would have a line from here all the way up there for the closed, all right? But it's the Haworth projection that shows it as the ring structure. All right, so again, you're going to have to look at what we call the penultimate carbon. So is this the D or the L form? Penultimate means second to last. D, because the last chiral carbon, which is going to be the second to last carbon on this one, has the OH to the right, putting the carbonyl to the top, right? This is the only way I'm going to look at it. I'm not going to screw you up by like flipping it around. All right? I'm not going to do that to you. So this is the D, biologically active. L sugars are not biologically active. And it's the opposite for amino acids, bless you. It's opposite for amino acids. Which ones are biologically active? For the L's are biologically active for amino acids, just to screw you up. So this is a D monosaccharide, and it's an aldo heteros, right? The 4. 1, 2, 3, 4. Think of my weird anxiety making. Okay. Now we can do some weird things with sugar. Here, diastereomers are connected the same, non-superimposable, but not mirror images. That's a lie. Yeah, I'll say that again. Diastereomers are connected the same in space, right? They're connected the same. Like this second carbon has a hydrogen and an OH. The third carbon has a hydrogen and an OH. They all have the same number, the connection is the same. But they're neither mirror images nor superimposable. You get this when you have more than one chiral center.
Because of not having a chiral center?
No, when they have more than one. So you can see that carbon number 2 and carbon number 3, on both of them are chiral centers, where they're mirror images on carbon number 2, but they match up on carbon number 3. So that just screws it up. Now, this messed me up in a big way. When I learned biochemistry, I thought, like, say, let's take this sugar, diastereomers, and I thought, well, to make the L, I would just switch the position of the OH on that one that defines it as the D or the L. No. It's the entire molecule's mirror image. So we have lots of chiral centers on our sugars. And so here we have diastereomers. L-erythros is the mirror image of the entire molecule, not just at that carbon that defines whether it's D or L. It took me until I taught this class to figure that out. I must have been chit-chatting in class. And really, in my research, I didn't do work with sugars. What sugars were interesting to me was that on antibodies for recognition, you have short little sugar chains all over the antibody. And so we needed to characterize those sugar chains and make sure that they were consistent when we were producing the antibodies. So that's what I cared about the sugar. So, but when you teach something, you really learn it. So again, here is D3-ose and L3-ose. Again, they're mirror images of the entire molecule. Yes, go on.
Why don't they have the standard names?
A standard name, because you can have an aldo tetrose be many different things. It doesn't define where the OHs are, on the right or the left.
Either like ose ending, does that mean
Sugar.
it's not enantiomers or diastereomers?
No. The ose ending just means a sugar. The ereth just is someone's whim. All right? And the D means that this is on the right. And so what they did is they identified or named this sugar that they found somewhere, right? And then they said, okay, the L is going to be the mirror image of the entire thing, not just in that last carbon. Okay, now we're going to start talking about the form that sugar monosaccharides are normally in, and they result from a reaction from the bottom part of our sugar reacting with the top part of our sugar. And what we have is a cyclization process. There's a lot of alcohols, right? There's a lot of OHs all over our molecule. Well, those OHs can act as nucleophiles because they have lone pairs. And then we have a carbonyl on every single monosaccharide, right? Carbonyls are susceptible to nucleophilic attack. That carbon is going to be partially positive. So we have a nucleophilic attack between the OH on one of the other carbons to the carbonyl of either the aldehyde or the ketone. Now remember, when there's a nucleophilic attack, we make a new covalent bond. When we have a nucleophilic attack, like we did in our chymotrypsin, where the serine nucleophilically attacked the carbon of that peptide bond, it made a covalent bond between the serine oxygen and the carbon of our substrate. Here, we're going to make a new covalent bond between the oxygen and the carbon of the carbonyl. We call it a hemiacetal if the attack is happening to an aldehyde, and a hemiketal if the attack is happening to a ketone. Now, once we have done this attack, it's no longer a double bond oxygen, and we have this cyclic ring now. The carbon that used to be the carbonyl now becomes what we call an anomeric carbon. Really important. The carbon that used to be the carbonyl now becomes an anomeric carbon. So it's either going to be carbon number 1 or carbon number 2 in our structures. And that is going to be an anomeric carbon. Now it becomes a new chiral center, right? Because we have 4 different groups bound to it. I like to put a little R prime on one of these because this R is different from this R. So it's going to be maybe R prime prime. I don't know. It's different.
Why is there no leaving group?
Why is there no leaving group?
Yeah, is that just like an intermediate?
Because the double bond is the leaving right here. It goes to a single bond, and we pick up a hydrogen. Okay, so this is that reaction we just saw on the last page. So the oxygen on a alcohol attacks the carbon of a carbonyl and makes a new covalent bond. If it's an aldehyde, it's called a hemiacetal. Now this is the Fischer projection of our sugars that have been cyclicized. Okay, so you can see what happens is carbon number 5 normally, if you have a hexose, is going to then do the attacking of carbon number 1 or 2. So if you have a hexose, the last chiral carbon's oxygen is going to be doing the attacking. I think it's easiest for you at this point to look at the Fischer projection to make sense of what's going on. It's kind of a weird long bond, right? But it's the oxygen that used to be here on glucose is attacking the carbon of the carbonyl. So this carbon number 1 used to be a carbonyl. Now it's just an OH.
Wait, can you say that again? The first carbon attacks? Or
No. The oxygen on the 5th carbon. It's this oxygen right here. It's right here. It's just a weird, doing it in the Fischer projection is a weird way to look at it. But that oxygen on the 5th carbon attacks the carbon that is the carbonyl. The carbonyl is no longer there because of that nucleophilic attack. It now becomes an OH. The Haworth projection is a little bit more realistic, a little less weird. And once you guys are ready, I'll start with that. All right. You guys have probably seen your sugars like this before in these cyclic. But we're going to look at them, how they form. So, all right, this is a nice big tree, all right? Nice big tree. What we're going to do is take this tree and have it fall down this way. It's going to fall down on the floor that way, all right? So we fall down, all right? This is carbon number 1. Right there, carbon number 2, carbon number 3, carbon number 4, and then we're going to take the tree and take the bottom of the tree and curl it over. All right? So then we're going to take this and curl it over. This oxygen, do a little circle around this. This oxygen is going to be attacking that carbon. So this oxygen right here on carbon number 5, that is attacking carbon number 1. The oxygen on carbon number 5 is attacking carbon number 1. So here you can see this is carbon number 5. The oxygen on carbon number 5 is doing the attacking. Carbon number 6 likes to dangle out there. It's going to dangle. So, all right, now let's take a look at this. If it's fallen over like a tree, this OH is going to be into the ground, right? It's going to be on the bottom. This OH is going to be up top, right? This OH is going to be down on the bottom if it falls over like a tree to the right. And this OH is the one that's in the ring. So just by starting out with your Fischer projection, remembering right, left, right, right, that's all you have to remember. Aldo, hexose, right, left, right, with the OHs. Aldo, you start with your aldehyde. Hexose, you draw your 6 carbons. And then the last one, there's no right or left because it's not a chiral carbon. And then you do right, left, right, right. You guys got that? Go home and do it tonight so you remember it, okay? Now, why would this oxygen doing the attacking, why wouldn't this one or this one do the attacking? Those of you that have taken organic, a full year of organic should know. How many members do we have? 6. Nature likes 6-membered rings. And we'll talk about that in a little bit. But nature likes 6-membered rings. The smaller the ring, the more strained it is. 5 is okay. 5 is okay too. But 6 is just, nature really likes it. 7, kind of weird. One too many people, not a good party. You know, it's just really, you know, when you have that extra person at your party, yeah, it just doesn't fit in very well. No. So anyway, I'm so sorry. It's so weird. So anyway, nature likes 6-membered rings. That does a couple things. It leaves carbon number 6 dangling out there. When we look at our reactions, things that are dangling are going to react. You have it dangling off of a ring, it's out there going, I'm ready to react. I'm out there. Okay? So it's dangling off there. All right, so now if you remember the tree falling over and then curling the tree around, the oxygen doing attacking. So look at this, guys. This carbon is carbon number 1, right? It used to be the carbonyl. Now if you look at this, we've already dictated where the OH is going to go on carbon number 2, 3, and 4, right? Because the tree fell down to the right. But on carbon number 1, there's nothing to say where the OH should be either down or up. And in fact, it's a 50-50 chance if it's down or up. And so when we do that, it's going to be either, if the OH is down, it's going to be alpha glucose. If the OH is up, it's going to be beta glucose. Birds are up, ants are down. Birds are up, ants are down. So alpha, the OH is going to be down. See, it's worth it to come class, right? OH on the top, bird is up. Now, I try not to on the exams to flip these around like pancakes because you can't flip them around like pancakes. But if you see the dangling number 6 pointing up like this, and then you look to the O to the right of that, so right of carbon number 5, that O, the one that is the carbon after the O. So you look at carbon number 6, find the dangly one, and say, okay, then the oxygen in the ring. The one to the right was the one that the oxygen attacked. This is our anomeric carbon. So it's anomeric because it used to be the carbonyl, and it can either be alpha or beta. Now in nature, what happens is, so my arms are the Fischer projection, or the open chain form. And so here, what happens is, in nature, if you have a solution of glucose, it goes like this, and then like this, and then like this, and then like this. So it closes and opens and closes and opens. So it does that. It spends most of the time in the closed ring form, the cyclized form, but it does spend some time in the open chain form. But that's why we have pretty much equal amounts of alpha and beta in a solution of glucose, and but it can open and close and go back and forth. And we're going to find out that in some structures, you can only have the alpha glucose. And in other structures, you can only have the beta glucose. Now, notice that here in the open chain, we just call it glucose. And in the closed chain, we call it pyranose because it looks like pyrin or pyrin. That's how they came up with names. Hey, this looks like this molecule. Let's call it that. All right. So this carbon number 1 is our anomeric carbon. The relationship, the alpha, ants down, birds up, the relationship to each other is that they're called anomers. So I have the right to ask you which, identify which carbon, I'm given a structure of a sugar, is the anomeric carbon. So this is our 5 and 6 membered rings. Most commonly, they're written where the anomeric carbon is to the right and the carbon number 6 is up here. Beta. Beta means OH is cis pointed up, cis to carbon number 6. And alpha means that it's trans to carbon number 6. So this is beta, and this is alpha. Now, I'll end on this. This is why nature likes the 6-membered ring. It's because our Haworth projection is what we draw it as, but reality is it's either the chair conformation like this. This is really what it looks like in space. Or what is the other one that's not as common? Boat, where this bottom one is up. So this chair conformation actually is in space. It makes those groups as far apart as possible. So in nature, it's not really a ring, but we're going to draw it like this all the time. So, but this is why nature likes 6-membered rings, because they form this chair conformation. It likes to spread out. And so again, here's our Fischer projection of the cyclized form, and here's our Haworth, and then this is what I'm going to draw, abbreviated. I'm just going to show where the OHs are.